Okay, Dr. Maria Molina gave a very nice start, so I'm going to pick up from where he left. But in staying with the theme of this plenary session, I'm going to first start at the reductionist approach, try to understand the system as much as we can. Then you will know that I fail, and then I'll switch to bringing in the complexity of the issues. And as I'll show you, the problem with that is there's no analog we can go back to. So to me, the title of this session just perfectly set. So let me just go to my home base. I'm trying to. So I show here the sun on the left, the inner planet Venus, then, Venus, Earth, and Mars. For my PhD work, I looked at the energy budget of Venus and Mars. And through divine intervention, I could not get a job in that field, studying Venus and Mars. So out of sheer desperation, I started applying. I landed on Earth for a job. And that was the NASA center. So what I'm showing here on the right arrow is how much solar energy we receive, each planet receives at the top of the atmosphere. Just focusing on the Earth is about 340 watts per square meter of the Earth's surface. The albedo, or the percent of energy reflected, is shown there, which is 29%. So then the net energy reaches the planet, heats the planet and the atmosphere, and then it starts radiating us infrared. So this process of incoming sunlight, outgoing infrared energy goes on till the two balance each other very close. So that's what determines the climate of the Earth. If you look at the surface temperature of the Earth, it's about 288 degrees Kelvin. So now let's ask ourselves to understand the greenhouse effect. Why is Venus so hot, 700 degrees Kelvin? If you look at the top of the atmosphere incident radiation, you would say, aha, it's a no-brainer. Venus is closest to Earth. It receives twice as much sunlight, so it's hot. But then what you see, Venus is so 100% cloud cover, it reflects 70% of the sunlight. The actual energy received by Venus is only 200, less than Earth. So solar energy is not the explanation for why Venus is hot. Venus is hot because of the greenhouse effect. It has a million times more carbon dioxide and other massive amount of sulfuric acid droplet clouds. So we know greenhouse effect can run away. Okay? So in fact, look for extraterrestrial planets, one is looking for exact distance between the sun and the Earth so that they think, but that's not the only determinant of climate change. So now let's go to the next thing, understand how the greenhouse effect works. This was my interest when I moved into looking at the Earth after my PhD in '74. I was fortunate that Langley Lab had a bunch of engineers who were brilliant in making radiometers. So I proposed to them this Earth radiation budget experiment. And on the right-hand side, Dr. Molina has already covered it. The incident solar energy is between, 1/10 of a micron, about 4 microns from UV, visible, and near infrared. And the energy Earth gives out is long wave of 4 micron. So we built cavity radiometers, self-calibrating. We would look at the deep space and look at inside as a black body. So it's one of the first calibrated instruments of the radiation budget of the planet. So what I proposed there is that using the scanning telescope, I wanted to understand the atmospheric greenhouse effect. So let's look at the holes between clouds and find out what the atmosphere is radiating, and then get the total radiation coming from the cloudy region and try to figure out what's going on. So therein is our understanding of the greenhouse effect of the Earth. This is direct measurements. And to you, it's not an analog. I would give you as a metaphor. If you stay with that metaphor, you could follow the complex story I'm going to weave. I think of the way the greenhouse effect works is like a blanket. On a cold winter night, the blanket keeps us warm, not because the blanket gives us heat, it traps the body heat. That's exactly how the gases behave. They trap the heat, infrared energy coming from the Earth. So I was interested to see how thick that blanket is and compare that with how man or human beings are adding to that blanket. So you see that the radiation coming from the surface of the Earth, we also determined that, that's about 396 watts per square meter. Keep in mind the energy from the sun is 340. We are radiating a lot more than that, okay, because there's an extra energy source, that's the greenhouse gases. What escapes to space is 265. So the thickness of the blanket was determined within 2 to 3 watts per meter squared for the first time. So that's 130 watts. And as Dr. Molina beautifully talked about it, it's amazing that blanket of absorption is not by oxygen or nitrogen, which is the dominant gas. It's by trace gases. Gases whose concentrations are in parts per million to 1/10%. And I say that because skeptics repeatedly say, oh, CO2 is few parts per million, cannot do anything. So the infrared absorption doesn't care about the mass. It's more the transition probability. These are really vibrational, rotational transitions of the molecules. So 130 watts. So how much have we added? And again, as Dr. Molina pointed out, that's basic quantum mechanics. All you take is temperature and humidity profile from the atmosphere, and then the quantum mechanical parameters, you have that energy trapped. So that energy trap, we know within 10 to 15%, which is 3 watts per meter squared. So this is what we have added. Okay, so we basically thickened the blanket by 2.5%. And there is very little controversy about that. And you know also from the basic theory, the paradigm, energy balance paradigm, incoming sunlight is balanced by outgoing infrared. And this has been happening, this balance. Then comes Mr. James Watt. I don't want to put all the blame on global warming on Mr. James Watt's steam engine, but still, fossil fuel exploration started. And the blanket was getting thicker. Not as much was going out as was coming in. So the planet has excess energy. Now I know the 3 watts. The other thing I want to walk you through is, how do we know how much the planet is going to warm? With just 3 watts, will it cause 1/10 of a degree warming or 10-degree warming? Okay? So the basic thing we can do is, let's pretend the planet is extremely dissipative, the lowest assumption we can make. It behaves like a black body. It radiates energy as black body. It doesn't. It's less efficient than black body. If you assume that, then it takes that sigma t power 4 becomes, if you differentiate it, is 4 sigma t cubed, and that's about 3.3 watts per meter squared per Kelvin. In other words, the planet can get rid of 3.3 watts for every degree warming. So you take that number, then you would get this 3 watts should have heated the planet by slightly less than a degree. Okay? But there is one fundamental thermodynamic constraint which we cannot escape. We call that water vapor feedback. I wrote the equation for the vapor pressure of water vapor. It increases exponentially with temperature. How do we know this to be true? The nature satisfies this, particularly in the latitudes you live in, the extratropics. The winter becomes cold and dry. Summer is warm and humid. The first order determinant of that is that equation, vapor pressure. Okay, that's why the cold, particularly when you climb up, it gets dry because you're losing e to the minus 5400 by temperature. The unit is Kelvin. In fact, I've shown you in a cartoonish way the water vapor density at the surface from polar region to the tropic. You'll be amazed. The difference is factor of 40. There is 40 times more water vapor in the tropics than in the poles. We know that, okay? So I was curious, can I use my radiometers to pull out that feedback effect? Is it there? It's a little bit of a complicated figure. Fortunately, the planet, this is my analog to pulling the feedback. The planet does a spectacular experiment. Every year, when you integrate over the whole pole to pole, North Pole to South Pole, the July is warmer by about 4 degrees than January, for varieties of reasons. But this is an established fact. And I got millions of observations, satellites and this. So we said, if this is true, 4 degrees, is also July more humid? So on the right-hand side, I honestly do not believe any in situ measurement, the balloon measurements. All of our balloon measurements of humidity and temperature are for weather purposes, and they're not calibrated. These are microwave radiometers, and what it shows, as the planet warms, the humidity increases, almost exactly what was predicted by thermodynamics. Then I said, oh, my radiometer should show that. So remember, I pull out the energy escaping, so with my radiometers, I watched it over a period of 5 years. And on the left-hand side, you see how the blanket thickens. That is the greenhouse effect, increased by 14 watts from February to July, 4 times the signal of the human greenhouse effect. So when I include all this, so now I know the feedback quantity. As temperature increases, how much does the trapping increase? So that's what I get, that the planet, with just the black body radiation and the water vapor feedback, can radiate about 1.9 watts per meter squared per degree Kelvin. Remember, it has to get rid of 3 watts. So the warming it has to have is about 1.5 degrees. So we know this number completely independent of models. Then we went back and checked with but 20 climate models. It was amazing. They came within 10% of this number we had inferred independently from satellite data. So I go to this. So my prediction, amazingly, this simple thing I went through had not been done. So it was so simple, I didn't even want to publish it. But then I decided I have to. So we published in 2008. And what I want to show you here is where the uncertainty comes in. When I say 1.5 degrees, you can ask, what is the uncertainty in that? So that is the probability distribution function I show. Okay? So the models come up with more than 1.5. If I use the model results, it should be 2.5 degrees. The reason is other feedbacks involving the sea ice, albedo, cloud fraction. I'm going to touch on that. So in a sense, I have no problem with what the skeptics say, the warming is going to be a lot less. It is allowed in our probability distribution function. There is, of course, a 5% probability we may have overestimated it. And there is a 10% probability we have underestimated. The warming could be twice as large. So that's the world we live in. And look at the predicted warming. Observed warming is only about 0.6 of a degree. So you can ask, where is this 2.5 degrees? Where did it go? Okay? So let's a little bit look into that. Another thing I want to mention to you, it has not come up in this. There has been about 6 major predictions have been made, starting from Arrhenius to about 1980. I'm showing you my paper. We had almost predicted everything we are seeing. Okay, I wish I had time to go catalog through. The water vapor feedback was predicted by Arrhenius, Svante Arrhenius, the famous Swede, who is the father of physical chemistry. Okay? Later, Manabe revisited it at Princeton in '67. It was my fortune to show that it exists. But because of this, in 1980, I teamed up with a famous meteorologist and did a stochastic analysis of variability in the system. And then we brought in this conceptual model and made a forecast. I have no time to run through this analysis. We predicted if our theory is real, valid, we should see the warming by year 2000. We gave a specific year, okay? And as you know, this is the IPCC finding, but Dr. Maria Molina talked about the IPCC. This is our best reconstruction of temperature record on the planet. And if you watch around 2000, that's when the signal came far above the noise, the 2 sigma, the 95% probability. There are others who claim to have seen the warming. They turned out to be right, but you could not have made that statement statistically significantly till 2000. That's when it went outside the 5% probability. So moving on to the next. Let me focus on what's causing this 3 watts per meter squared trapping. I said the blanket is thickened. What is the chemistry of that blanket? Okay. Until 1970s, we thought carbon dioxide was the only greenhouse gas which is contributing to warming. And I didn't know the literature. If I'd seen the literature, I would not have done this work. So I started from scratch, started looking at the chlorofluorocarbons. And the reason I was looked at the CFCs, 2 reasons. Before I came here, I had a job as a refrigeration engineer in India. My job was to prevent the CFCs from leaking from the sealed units. I failed in that. And CFCs kept escaping. And Molina, Rowland, and Crutzen got Nobel Prize from this leaking CFCs and their impact on ozone. But my work was on the infrared properties. I was shocked to find addition of 1 molecule of the CF2Cl2, CFCl3 had the same effect, infrared trapping effect, as 10,000 molecules of CO2. Here it is, we have unleashed a super greenhouse effect. So I had predicted by then that by now, CFCs would have become a major greenhouse gas. So thanks to the Molina, Rowland, Crutzen's work, CFCs are banned. In fact, this is a major success story. We have already avoided a climate disaster. So quickly after this work, numerous gases were added. So this is where we stand. I'll explain to you this Venetian mask. I went to Venice 5 years ago. That was my metaphor I was looking for. So I'll come to that. So when we talk about climate change, we just talk about CO2, which of course we should. It's the major issue. It could be a disaster 50 years from now. But it turns out about 40% of the increase in the thickness of the blanket is not from carbon dioxide, but from methane, comes from natural gas leaks, halocarbons, CFC is part of that, nitrous oxide from fertilizer, and ozone, greenhouse effect. Ozone we know it as a pollutant. In fact, its major role was identified in a joint paper with Paul Crutzen, myself, and his graduate student, Jack Fishman. So the reason that 40% is important, I'll come to soon, therein lies a solution to get out of this mess we are in. The third circle was also recent work, last 10 years, black carbon. And it was being talked about. Black carbon is basically the soot which comes from diesel combustion and fires, etc. And modelers have done this, but there was a major experiment done, joint experiment between US, which was led by me, and Europe, which was led by Paul Crutzen, and India was a major player in this. In fact, Dr. Kasturirangan helped start this project in India. Dr. Mitra was the chief scientist. So that black carbon has now emerged as another major contributor. The key thing I want to mention is black carbon does not trap as much as greenhouse effect. It is the most efficient absorber of sunlight that we know. That's why it's black. That's why, Dr. Cianaro, I'm very worried about this carbon. This is basically graphite carbon and carbon clusters. And there are experts here, or Pius Medlawardi, Yuli Pershalis, some major work done in this area, as well as Maria Molina. Anyway, so suddenly this is there. So the question you should ask is, where is the 2.5 degree warming? We should have, I'm predicting it should have been there. It turned out, so now going to the blanket we have thickened, and think of the black carbon as smoke in the blanket, not letting sunlight come through. It's heating the blanket directly. It's made the blanket an electric blanket. Still, there was something there by sheer dumb luck. As we were putting this climate pollutants, we've been emitting reflecting particles, sulfur, from coal combustion. So the sulfates has been well documented. You can think of the sulfates as mirrors on the blanket. So we have made into a complicated blanket. There's greenhouse gases, it has smoke, and it's got mirrors. I have to be careful. The skeptics normally, when they say, oh, we know Ramanathan, he talks about smokes and mirrors. But this just I'm using as a metaphor here, okay? So when we take the masking effect, which is about roughly 50%, the issue is we have not seen the real beast. When you factor in there, then you can explain why the planet has warmed only 1/3 of it. So I just want to conclude it with my forecast. This was done, I'm hoping, fortunately, what I'm forecasting could be seen in the next 20 years. So if I'm still alive, I am expecting this academy to say, what you said did not happen or did happen, okay? So the first one, remember I forecast in 1980 we will see the warming in 2000. So I'm saying the blanket is already thick enough to heat the planet by 2.5. This is a huge dilemma because Obama and all the leaders said we should not let the planet warm by more than 2 degrees. So that's the limit. So how can we do that? Okay? And so the other is we are going to reach this 2 degree warming, not end of the century, by middle of the century. It's a lot more imminent than we thought for an important reason. Sorry. Yeah. See the mask? We are rapidly unmasking. Because of concern, the same sulfates, particularly this move started from Germany and Sweden, because it was leading to acid rain. The sulfates would wash out the sulfuric acid, and forests were destroyed, ecosystem health effects. So we have cut our sulfur emission by almost 30 to 40% in Europe and North America. I'm not blaming this cleaning up for the warming, but it is contributing to the acceleration of the warming. And the reason we have not accelerated as much is because as the western region is cutting down its emission of sulfur, the emission of sulfur from India and China, others are increasing because they are going through the development process. So again, by sheer dumb luck, we are not seeing the rapid acceleration from the unmasking. Stopped advancing. Yeah. So how do we get out of this? Fortunately, there is still a solution. The first thing is we have to thin the blanket. We cannot thin the blanket by reducing CO2 because it's long lifetime, 100 years. So that is in fact the most deadly part of CO2. Once you have released it in the air, there's very little you can do on timescales of 500 years. Whereas the other gases, their lifetime is between weeks to decade. So if we cut down soot emission today, we can. The diesel is a major source in Europe and North America, and there are filters available to cut it to by 99%. So we can, this will go away, okay, overnight. Same thing with ozone within months, methane within 10 years. So we have a chance to cut down that 40%, delay this onset of the 2 degree warming, give the world some time to adapt to the climate change, because we must prepare ourselves to adapt. And so this is sort of our conceptual model simulation. The red line is the line we would have been, the planet would have been, according to this model, which I said was just nothing to do with any of this 4-dimensional climate models. It's basically what I did use from observations. The red line is what we would have been without this mirrors on the blanket. So by sheer dumb luck, we have saved the planet already. But the figure is, it's become a toxic, most deadly blanket. We cannot just dust off the mirrors. As we dust off the mirrors, we have to thin the blanket. So it has to be carefully done. So the blue line is what we will be if we cut CO2. You see that cutting CO2 is not going to still prevent the 2-degree warming. The only way we're going to, again, it's based on my work inference. It's not a consensus yet. You can push it by 30, 50 years by cutting down the SLCPs. Fortunately, this work caught the attention of, and then Dr. Molina and us teamed up, and we published a paper later in 2009, and now UNEP has accepted this, and Hillary Clinton started a major coalition. About 25 countries have joined this, focusing on the SLCPs, and the secretary is in Paris, and we are now talking with German scientists and government to see if they would join the coalition. So I wanted to talk about what is this magic thing about 2 degrees? Why are we worried about temperature change? If you look at the current distribution of planet temperatures, the warmest ocean is the Indo-Pacific Ocean. I have a yellow circle, and then again tropical oceans in the Atlantic. That is where all the hurricane genesis takes place. Hurricanes, cyclones, their genesis, they are born in warm water. We know this. I still don't understand why we are arguing, oh, is the warming causes hurricanes? We know hurricanes, but why is that? It's going to the thermodynamics. The energy for the hurricanes is driven by evaporating moisture from the ocean. It condenses in the air as rain, and that powers the hurricane. You're just basically taking sunlight from the ocean in the form of water vapor and dumping it. And it's interesting, this Sandy, for example, the warm water was anomalously warm by 2-3 degrees. I have no problem with that. But the global warming, the Atlantic has warmed by 0.5 to 1 degree over the last 50 years. So out of this 3-degree anomalous water, at least 20% of that is coming from long-term climate change. But what drives a hurricane is numerous other factors. That's where the complexity comes in. So we are worried about intense weathers. Okay? And the second thing we are worried is when it rains, it'll pour because the atmosphere holds 10% more moisture for every degree warming. So when you let the planet warm by 2 degrees, you're assured your rainfall will be more intense by 10 to 15%, just from thermodynamics. Okay? The other reason for 2-degree warming, this is a civilization, we have to think about it seriously. I've showed 3 plots. These are all done by paleo guys. The right one is the current one, but let's focus on the last 50,000 years. As you know, the Earth goes through major glacial, interglacial cycles. Okay? On the leftmost extreme, the time scale is 3 million, and you can see how the system, like a clock, goes to the glacial, interglacial. I'm going to pose a question. We all know the Earth system is complex, nonlinear, chaotic, but it has been beating this pulse regularly. It always knows to come back. But look at the last interglacial. We've been enjoying a steady climate unlike any we have done over the last 6,000 years. And there are many anthropologists are suggesting, is that why civilization could advance so rapidly? So we have not had much climate change. We sort of got spoiled. And now what we are talking about is taking that middle curve, push it by 2 degrees. There's no analog. Had we done this fossil fuel pollution during the middle of an ice age, we'll all be celebrating. The problem is we are doing this dangerous experiment during an interglacial. So when the planet moves 2 degrees, honestly, I do not trust any models, including all the observational deductions I have done, because they're all based on looking at analogs. There is no analog for this 2-degree warmer climate. So I'm going back to this. I'll just finish this rapidly. The advantage of the short-lived climate pollutants is that we have a solution. It's been done before. For example, California cut its soot emissions just in the last 20 years by putting filters on new vehicles. Okay, this soot from Europe and North America is one of the major sources for Arctic sea ice melt, so we can stop half of that. I want to go to the bottom one, cooking with traditional mud stoves. And I don't know how many of you are aware, but 2.5 billion have no access to fossil fuel. We as a society, we have left behind about 40% of the population to fend for themselves. They don't have a light for electricity, heating, and cooking. And it turns out this cooking indoors is now documented. WHO kills over 2 million. And about 15% of the global warming could be stopped by cutting down soot emissions. Also melting of the glaciers in the Himalayan Tibet region and Arctic. Okay, so taking this, and this is based on a paper we published in Nature, teaming up with a chemist. The left one is the simulation with all of the mud stove emissions. On the right, we just replace. In China, it's mainly done with coal. In South Asia, it's firewood and cow dung. 2/3 of the problem just goes away. And there are also about close to 80 million crops damages from these smoke. So we started a pilot phase experiment teaming with a major NGO in Terry. And I want to say my daughter, who is a wireless technologist, and she designed cell phone instruments so that we can make mass scale measurements. So we measure many huts inside and outside. I think we have convincing proof. You can see the red line is the indoor concentration of black carbon. When the woman starts cooking around 4:30 in the morning, it increases, it peaks, and then it dies down with an e-folding time of 2 hours. And then she comes back from the field, starts cooking around 4, picks up. And then the blue line is outdoor measurements. You can see how it follows like a beat. Okay. By the way, this heating we are talking about, if I measure Italy, Rome would be a major black carbon region in Europe. For example, Frankfurt, Germany, it'll be 1 to 2 micrograms. That's considered major. Here we see 50 to 60. And yes. So fortunately, there are technologies available to cut this, still using firewood, because remember, cow dung and crop residues and firewood, if you harvest the forest properly, are still renewable fuels. And we found just putting a small fan in the stoves, the force trap, you just wipe out the pollution. So it's a problem waiting for solution. The question is, can these people afford it? Because these stoves cost about 60 to 80 euros. So we have started a program and asking for donations so that this could be. An Indian government has a major program on cook stoves. I want to just conclude. So far I made look everything we understand and we know how to do it. So where does this story fall apart? Okay. That's with clouds. Dr. Molina already alluded to that. This is again, I think one of the first studies to publish what are clouds doing to from observations. Well, clouds on the one hand reflect sunlight, cool the planet, but they're also like a blanket, infrared. We know on a cold winter night, a cloudy region is warmer. Okay? So we figured out how to add the two. And what we found was clouds have a major cooling effect on the planet. The beauty is this cooling effect comes from extratropical storm track cloud systems, not from the tropics. So it's like nature has 2 white umbrellas, one over the Arctic, one over the Antarctic, protecting us. If those clouds had not been there, that's equal to about 10 to 20 times the CO2 concentration. So there's a huge leverage there. And that's what our future is going to depend on. Are those clouds going to contract or expand? We have done an analysis over the last 20 years. This is a Swedish postdoc. We are finding, unfortunately, the extratropical clouds are shrinking. Okay, there are dynamical reasons to figure that out, but the story doesn't end there. And what is completely missing, in my thinking at least, and in our models, is the role of the biosphere. You know, the atmospheric constant is CO2, methane, nitrous oxide. It's all governed by biota in the soil and the ocean. Case of clouds, one of the major sources of nuclei, remember water doesn't spontaneously condense because of surface tension. So it needs something which will weaken that surface. It needs a foreign substance, a nuclei. In the oceans, that nuclei is provided, one of the nuclei is provided by dimethyl sulfide. Organisms, or they emit more dimethyl sulfide and produce more low-level clouds. Okay, I think in my mind, that's all we are left to hoping. So I want to finish this talk, go back to the story that if the skeptics are right, we would be on the left extreme of this curve. Not much to worry. So I am honestly praying for this, that the whole climate science is wrong. The few skeptics, the dentists, as Polino calls, have the right diagnosis.
Excuse me, problem with this, can you speak there?
Yeah, okay. I'm almost done.
Yes.
So I feel I'm now crossing the line from being a scientist to advocating policy. I feel we should plan for the 2/3 probability that we are in the middle of the curve. Okay, the extremes, on the right extreme, I don't see how we can plan to do anything. We are too late to prevent such a disaster. But we can prevent it with the short-lived climate pollutants, uncutting CO2. If it so happens, our truth lies in the middle of this curve. Thank you. Oh, one last I have to say. Going back to the pray for this, I want to thank our Chancellor, Rondo. When we held this meeting in the fate of the mountain glaciers, we conclude this declaration, and we have a prayer there. Right? Let me read the last one. We are committed to ensuring that all inhabitants of this planet receive their daily bread, fresh air to breathe, and clean water to drink, as we are aware that if we want justice and peace, we must protect the habitat that sustains us. This was signed by all the scientists attending this, and then the believers among us, I'm one of them, ask God to grant us this wish. Thank you.